I really appreciate, like the previous speakers, the opportunity to talk to you today. Physicists ask what kind of thing this universe is. They define physical systems and try to characterize them. Biologists ask themselves what it means for one of those physical systems to be alive. And we in AI, we ask ourselves what kind of information processing system can ask such questions. This is a quote from the Handbook of AI by Avron Barr and Ed Feigenbaum, published in 1981. And I think to this day it is the best stand-in for a definition of AI that I've seen. I'm going to talk about more about this in a second. First, in particular, in response to the things that we've heard this morning, I would like to interrupt my own talk and talk about why it is important to have a definition of AI. We have heard this morning that AI is equivalent to data science, equivalent to machine learning, equivalent to autonomous driving, and all of these things. I think it is a fundamental mistake to equate these things, because if we don't really understand what AI is, and I think we don't, I think none of us do, I don't either, we cannot devise policy. We cannot devise appropriate funding programs. We cannot predict the social impact of this technology as it develops. So I'm going to spend my presentation to try to approach an understanding of AI that is different from all the things I mentioned, data science, data mining, big data, and so on. So let's go back to what I just quoted from this handbook. An information processing system that can ask questions. Right? So this is also what the previous speaker said. There is an interaction between an agent and the world. But this interaction can be a simple measurement. Like autonomous driving, I have a camera, it measures light. I have a laser, it measures distance. Or it can be a real question. And I think we have a totally different type of information processing agent if this agent can ask a real question. Well, and it's not just asking, it's also being able to answer that question by interacting with the world and to derive new ways of acting in that world to achieve certain goals. That is, as close as I can get to understanding what intelligence is. And like I said, it's not what an autonomous driving car is doing. So it's about the quality of these red arrows that I think is particularly important. And so to me, robotics is the science of intelligent behavior. Right? And to me, that is very close to intelligence. So if in the remainder of my presentation, I refer to the loop, I'm going to refer to this thing, but with this special quality of being able to ask and answer questions. Let's look for a second at some of the acclaimed things of AI through the lens of, do these systems ask questions? This is 1997. Computer for the first time beats the world reigning champion in chess. I would claim this is an amazing achievement, but it does not qualify for an AI system. Fast forward 20 years, this was mentioned before, AlphaGo. It is the same thing. It is just a different game, admittedly a more complex game, but nothing has changed. If you think about the loop, there is no loop here. Right? The thing does not interact with the world. It prescribes the interface, and humans comply with that interface. So, two examples of amazing feats of so-called AI that are maybe not really AI. And it seems paradoxical that there are two people sitting in these pictures whose sole role it is to move the pieces. So this loop that I think is essential to AI, and that is the core of robotics, has been eliminated completely, and still we call this AI. I think this is a big problem. Well, is it really paradoxical? Yes, it is, if we take our own judgment. Humans tend to be impressed by things that are difficult to themselves. We're impressed by people that play chess because we probably could not beat them in chess. We're unimpressed by the thing that we call intelligent because all of us are intelligent. It has taken evolution 3.8 billion years to produce information processing systems like us. Chess and Go have been around, depending on which story you believe, for at most 2,000 years. So what is impressive is that 3.8 billion years of evolution have created a system that is also capable of playing chess, also capable of playing Go. But we're surviving in a world, we're learning, we're doing amazing things that we don't regard as important. And that to me is AI. And so one of my important messages to all of you is, this is, by the way, it's a named paradox. It's called Moravec's paradox. And it has been around since the 80s. The godfathers of AI realized this very, very quickly, that this paradox exists. And we keep ignoring it in making policy, in making research programs, in devising our own research. I think that is a big, big problem. So this is one important lesson. Next time you see news all over the world about the next more complicated game being now, dominated by a computer, and it's called AI, don't believe it. So let me make this more concrete. What could it mean to ask questions? And I don't think we should start by asking questions like, what's the meaning of life? We should start by asking simple questions. Well, they're going to turn out not to be so simple. So here's a question for you. This is a mechanism. The black square on the left is actually a plexiglass door, and behind it is a cashew. Now, you would like to get that cashew, and there's some kind of mechanism here that you need to open. Okay? Who has solved this? It's going to take a while, right? So there's a pin at the top you need to take out to remove the screw, to remove the pin, this metal cylinder, which is preventing the disc from turning. The disc needs to be turned so it can be moved over this pin. Then you can move the bolt to the side, and then you can open this. So I would view this as a sign of intelligence if you can solve this problem. And it is asking a vital question of the world: how do I get to food? Here is an information processing system solving this problem. It's a Goffin cockatoo, and you can see that this Goffin cockatoo doesn't hesitate. It just solves this puzzle. Okay? So we could debate, if there were time for discussion, to see if this Goffin cockatoo is intelligent. I believe it is. And if we can build robots that exhibit the same behavior, then I think this would be a sign of intelligence. And so we did. This guy, Alex Kachelnik from Oxford University, came into my office one day and said, "Oliver, you have to build a cockatoo for me, because I've been collecting amazing skills of animals for my whole life, and I don't know how they do it. And I have no way of opening their brain to take a look at it." Right? Let me make a side remark here. We've heard about the growth of storage, of information processing, of computational power, right? This bird has a brain that weighs 10 grams. You have a brain that weighs about 1.5 kilos. Okay, so there cannot be that much information processing going on in that brain as we have already going on today. So it's not how much computation, it's what computation, right? It's important what we compute. And we don't know what to compute. We're trying to throw more computation at things because we have no clue what it is, so we want to compute everything. We've got to be smarter, not more powerful. So this is the robot that we built, and we've tried to replicate the structure of this little puzzle for our robot. And I'm gonna fast forward here to stay on time, but in the end, the robot solves this puzzle. To get the equivalent to a robot of what the cashew is to the bird. Now, what have we gained by doing this? Right? I think what we've gained is a new way of deriving insights into what intelligence might be. We take something that we would call intelligent behavior from biology, we replicate it on a synthetic artifact, and all of a sudden we have new possibilities. We can open the brain, and we can change things. We can ask new questions of the system that we would not be able to ask of a bird. There's no more question of how motivated is the bird in a good mood, right? We have full control over this experimental system, and we can make very consistent and great experiments. And the insights from this then go back to the biological side, and they can form hypotheses about how birds do it that we can then test. And so we enter into a loop between understanding natural intelligence and creating artificial intelligence that I think ultimately will lead us to an understanding of what intelligence really is. In a way, following Richard Feynman's quote, "What I cannot create, I do not understand." So by creating artifacts that behave intelligent, that ask questions of the world, I think we can begin to understand intelligence. Now, this loop, I think, is critical. You will see this loop in the next 20 years over and over and over again. One important message is, think about what the arrows mean. Right? If it's just sensing something, it's trivial. A thermostat on a heater is sensing something. It has to be a question that we're asking of the environment. And it has to be a question that we answer by interacting with the environment. So that is my message number one. My message number two is Moravec's paradox. Right? The things that are impressive to us may not be at the core of AI. Right? Maybe there's no chess grandmaster here in the room, but we are all very highly intelligent beings. So yes, being able, and you could all learn to play chess unless you already know. Playing chess is a sign of intelligence, but the inverse is not true, right? So you can be intelligent without playing chess, and so we would like to understand the actual intelligence. So first message is this loop, and the quality of the loop is important. Second message is Moravec's paradox. Third message is there are a bunch of disciplines, not represented here, that I think have important things to contribute to understanding this loop. On the biological side, disciplines like psychology, behavioral biology, educational science, philosophy, neuroscience. All of these have something to say about how we should construct that loop. And then, the disciplines represented in this room, robotics, computer vision, machine learning, artificial intelligence, control. All of these disciplines need to come together for us to understand the nature of this loop. Thank you.